Good morning, everyone. What I'm going to talk about is thermal storage. Thermal storage is the one important feature that distinguishes solar thermal generation from other renewables like wind and PV. And the difference is the fact that we can store heat quite cheaply. And in this talk, I'll be obviously explaining why we need thermal storage and very briefly go through the options available to us and the current technologies, and then go to current activities with a focus on the activities we are doing in Australia, and particularly in my own University of South Australia as a part of a national effort in solar energy generation. And hopefully after that we'll have time for questions. Just like we have here in Morocco, as you can see, Australia and many other parts of the world have plenty of sun. But in Australia, we haven't got as many large generation activities using solar thermal. We have plenty of solar PV. For example, in the state I come from, which is South Australia, 1 out of each 4 homes have solar PV, and 40% of our electricity is generated from wind and mainly solar PV, but we have very little solar thermal yet. And we're already suffering from some of the issues associated with the inability to store renewable energy, and this is having some impact on the quality of the electricity we get. These are a couple of examples of real installations in Australia. The top one is a small research solar thermal generation facility in an institute called CSIRO. A few weeks ago, I was in the site of a company building 20 megawatt solar thermal tower plant based on small towers and small groups of heliostats. The company is called Vast Solar, and we're working with them on some of the storage activities. As I said, it's important to have storage because, as we know, the sun varies in its intensity from summer to winter and also from day to night. And what we find, particularly in Australia, is that this particular area here is the hardest, and this is where we get the peak demand when the sun starts to go down, particularly in winter, but even in summer, when everybody comes back home and turn on their large air conditioning systems, we have some issues associated with the peak demand. Just to put solar thermal storage in context, in comparison with a lot of publicity we've heard recently, and I'm sure you've heard as well, regarding batteries for storage of electricity, and to give you an idea of the cost comparison between electrical storage in batteries and thermal storage. You can see here the recent announcement of Tesla, where they are talking about the cost of battery storage being something in the region of $1 to $1.5 American dollars per watt hour of electricity. Compare this with the current costs of solar thermal, and we hear a lot of different costs from companies, but I'm here comparing the 2020 expectations for solar electricity, which is still $1 to $1.5 per watt hour. I'm comparing it with the targets we have for solar thermal. There's a program in the United States, some of you may be aware of, called the Sunshot program, where we are looking at $15 per kilowatt hour, not watt hour, kilowatt hour heat storage. And in Australia, we have a program for developing solar thermal, looking at, again, by 2020, reaching $20 per kilowatt hour thermal. So you can see that even after we allow for the conversion from heat to electricity, we still have a good order of magnitude difference in cost. So in other words, solar thermal storage would cost about a tenth of the electrical storage, and that's why we have the edge over electricity storage. There are many factors to look at in selecting an energy storage system. Obviously, the capacity, the lifetime of the system must last long enough. It has to be sized correctly. Also, it has to respond quickly to the requirements of the generation, because, as you know, we have a turbine that likes to operate at a steady rate, and as a cloud passes through the sky, we need to compensate for that quickly enough, as well as make sure that the storage provides more heat for the turbine when the sun radiation reduces. At the end of the day, obviously there are commercial factors that play a role, and particularly the cost of the system in comparison with how much benefit we're going to get from it. And when I'm talking here about what I'm calling the value proposition, it's not just the cost of kilowatt hour, not the cost of a unit electricity, but also when this electricity is available. So the cost of electricity during the peak demand, certainly in many countries in the world, is a lot higher than the cost of a unit of electricity when there's plenty of sunshine and very little demand. So that needs to be considered also in the sizing and selection of the solar system. And there are many components of this cost, including the material itself that we use for the storage, but also the containment or packaging material, the particular type of construction and geometry, or how we exchange the heat with the other working fluids in the system, the actual heat transfer fluids that bring the heat in and take it out, but also, and this is a minor thing, the last point is the cost of the actual space occupied. It's quite small in comparison with the vast areas of the heliostat systems and the other components for the solar. I think most of you are aware of this, so I'm not going to spend too much time on it. There are three options which are talked about and used in to various degrees. The current technology uses sensible heat storage, and it's simply heating a fluid to a higher temperature, and it's no different from heating water in our tanks when we use hot water in the home, except that we need to have a fluid which is capable of going to the temperature required, and also having the tank and the rest of the system and the pumping and piping systems which can cope with the material being stored and pumped. And this is the current technology, and here, here we have some of the actual systems in use in some of the, particularly I think this is a Spanish example, where we have a two-tank system where we have a hot and a cold tank, and we are when there is enough sun available, we just heat the fluid. The other method which I'll be focusing on is using the latent heat as a way of storing a lot of heat for a smaller volume and a smaller capacity, and I'll say a lot more about that. And finally, we have the thermochemical energy storage, which depends on a chemical reaction to happen. I'm not going to spend too much time on this. This is the classification, and it shows the various ways we can store heat. And you can see the sensible and the latent and the thermochemical. And, oops. So just overviewing very quickly the current technology. As I said, we have normally the current systems use a liquid, and it's just heating it up. In previous systems, oil was used, particularly synthetic oil was used as the working fluid, which is heated up. Now we have molten salts which go to higher temperatures, and we simply have two tanks, as I said before. But there are a number of developments to try and use other solids in particular. We had a paper in the conference about using rocks, but also other salts and even some metals and other residues of industrial processes are being considered at the moment. These are some examples of current technologies in use in working plants, and I believe in Ouarzazate the storage is going to be similar to this at the moment. I'm not going to spend too much time on them, but this is the current technology. As you can see, we have a two-tank system, and we get the heat from the collectors or the banks. And normally we're talking about heating from something like 290 to 300 and something degrees to 500 and something degrees, and then use that to supplement our heat. The current technology uses a salt mixture of these two salts. And as I said, we're talking about a range of temperature between 260 and 600 degrees. What are the limitations of this material and why there are issues associated with it? Salts are corrosive, and they need particular attention for the tank and the pumps and the pipes that use them, and we have to be mindful of that. And we have to use stainless steels of various levels to enable that to happen. The other problem, which is quite serious and causes a lot of extra cost and a lot of headaches to some people, is the fact that salts will freeze at temperatures around 200 degrees. And if the salt freezes, it's a big issue to try and remelt it. So often we have heaters put all over the place around the tanks and the pipes and the pumps to make sure that doesn't happen, and these heaters cost a lot more and require continuous attention. Also, of course, we have sensible heat in being used here, so there's a temperature range for the stored heat, which means that when we are utilizing it to generate steam, we don't get the best thermodynamic heat exchange between the two. Let me say a few words about the solid storage systems. As I said, they are usually very cheap, available materials, and some groups are looking at just using desert sand as a storage medium or some rocks. But also there are many other materials being considered, like fire bricks, industrial solid waste, as I said, and so on. And usually these materials are of high heat capacity, so they store quite a lot of heat and they are cheap. But there are issues associated with the thermal expansion of the material as it increases in temperature by many tens of degrees, and also the transfer of heat from the rocks to the fluids can cause some difficulties. And this is by no means a comprehensive list of some of the media being looked at and considered for storage, and there are lots of different ways of making this happen. I'll say a few words about thermochemical storage and then focus on phase change materials and latent storage. Thermochemical storage is simply making use of some of the chemical reactions which need heat to take place, then give away that heat when we go to the opposite direction. So we have to have reversible reactions, and when heat is available, go in one direction and then go back in the other direction and get that heat. It sounds easy, and there are many chemical laboratories working on different materials, and in principle it's a very good idea, and there are lots of advantages which we'll see in a minute. But in reality, there are more difficulties when you get to a large plant and want that to work for a long time without any difficulty. So the advantages, certainly we can have long-term storage. We can even consider seasonal storage if we want, because once we have the chemical reaction, we can keep those materials in one place and wait until we need to use them, unlike the thermal storage where we can lose some of that heat over time. They're very compact in terms of their energy density, much better than the latent and sensible storage. Good efficiency. Having said that, as I said, they are rather at the early stages of development, and there are not many real applications close to being commercialized. The systems are quite complex, and there's limited experience with operating them. There's always the potential of contamination of the materials reacting, and if that happens, obviously we have to start with new material. Also, this is one of the examples of using ammonia and converting it into nitrogen and hydrogen products. Also, this method is being considered in reactors to use sunshine to produce fuels from other materials. So to use the sunshine to break down some of the more polluting conventional fuels and use those fuels as renewable fuels. And that's certainly our dream. If we can do that, if we can use the sunshine to generate liquid or gaseous fuels and then transport those, it'll be a great thing to do. And there are some exciting research happening in this area, but we are a long way from a real working system close to being commercialized. So now I'm going to go back and focus on latent heat energy storage. And perhaps we've all used latent heat energy storage whenever we had a drink and we want to use ice to cool it down, because ice is a good and one of the first, certainly the first material to have been used for storage. We obviously take the heat away when the ice melts, and to make the ice, and then it takes away the heat from the surrounding fluids. So the concept is simple. All we need to do is to make this happen at the desired temperature, whether it's 500 degrees or 600 degrees. And we need to find the materials that will melt or freeze at those particular temperatures, and then the problem is solved. So how do we select a phase change material? I'll be using the letters PCM for phase change material. I hope most of you are familiar with that. So obviously we need to use the material that melts and freezes at the temperature we want our operation to be at. And this is one of the advantages of phase change material, because it stores and liberates heat at a particular temperature. That temperature can be designed to suit the particular application, and we can have a good temperature difference in either when we are storing the heat from our solar source, or we are transferring it to the power plant. Also, when we are selecting the material, it needs to have large melting, specific large heat of melting and freezing, so that we use the smallest amount of material and the smaller volume. There are specific technical and physical aspects. Some materials don't freeze and melt in a repeatable cycle, and after a few, maybe 50 or 100 cycles, they break down, and obviously that's not what we need. We want to make sure that this change of phase will continue for thousands of cycles for the duration of the plant. Some materials need to be cooled to lower temperatures than necessary, and we call that subcooling, and in some cases they call it supercooling, and sometimes that could be a problem, so we need to be in control of that. And one of the biggest problems with many of the phase change materials we're looking at is the thermal conductivity of the material, and the design of the vessel, which will enable a quick response in terms of heat transmission. There are others, like we need low vapor pressure. We need not a large difference in the volume between the liquid phase and the solid phase, to make sure that that doesn't cause problems for our container materials. Obviously, the material has to be chemically stable and compatible with the materials containing it. Also, I haven't put it there, but it has to be safe. We don't want fires to happen and so on at these temperatures. And we need to also make sure that the material, as well as the containing vessels, are cheap enough to use. So I think I've covered most of these, so I'm not going to spend more time on this, being mindful of the time. A lot of these problems are being looked into, particularly the issue of low thermal conductivity and heat transfer rate. This is being done by increasing the surface size for the heat exchange, by adding some high conductivity particles, or nowadays also nanoparticles are being used as means of improving the thermal conductivity. And I think we saw a paper in the conference on that. We are working on what we are calling dynamic PCM systems, where we are agitating the fluid inside the storage tank to make the freezing and melting happen more quickly, and we are calling it Dynamic PCM system. Also, we are trialing some direct contact heat exchangers, and for those of you who were present, I presented a paper 2 days ago on that, and that's another possible option. The other issue associated with long-term stability, obviously, the biggest issue here is to make sure that the material we are talking about or we're using is compatible with the pipes or tanks that we are using, and especially when we go to the higher temperatures, this becomes an issue, and there's a lot more work being done to avoid corrosion in particular. But also to ensure that happens, once we select a material, we need to cycle it through melting and freezing for up to a couple of thousand cycles before we can say it's suitable for commercial use. And we are doing a lot of that again in our laboratories. These are various configurations for the storage systems. Some of them I've talked about already, but some of them are simply the tube in a tank arrangement, or plates where, oops, we've done it again, sorry about that. Plates where alternate areas have the phase change material and the working fluid. And there are a number of other alternatives I'll be talking about in a minute. Having looked at the previous configuration, which uses oil or salt in the collection and storage side, and then steam in the generation side, I guess we need to think how we can make this more efficient, and the easiest way to do it, especially with the good development of tower systems, we have quite a lot of high temperature generation available now. What we need is to find storage systems and generation systems, turbines, which will cope with these higher temperatures. And as the engineers of you know, particularly the thermal engineers, the higher the temperature of operation, the higher the thermodynamic efficiency of the whole plant. And this is what we are striving for. We have a group of research institutions in Australia working on an 8-year program to develop a number of the components associated with this option, which we are hoping to work in the next few years. So looking at using, instead of other fluids, we are looking at using sodium in our receiver, and then we are looking at using supercritical CO2 as an option in the storage system and in the generation part. And between us as a group of institutions, we are working on separate projects to try and develop some of the components while we are talking to each other about how to integrate that into a full system, which we hope will be feasible in the not too distant future. And these are all the groups that work. As you can see, we are being funded by the Australian government through the Australian Renewable Energy Agency. And these are the universities and CSIRO who are a part of the what we call the Australian Solar Thermal Research Initiative. And also we have strong links with some of the US organizations doing research. Some of you will be recognizing some of these. I'm also happy to say, through an appointment of the leader of this initiative, Coming from Europe, we are now developing very good relations with particularly Spanish and other universities and institutions in the various areas. And certainly in my group we have very good relations with 2 Spanish universities, and we exchange visits and learn from each other, because obviously Spain has got more installations recently than many other countries. In my own university, these are some of the areas of research we're working on to make PCM storage practical and commercially possible. Certainly work on material characterization and property evaluation may sound easy, but many of these salts that we're dealing with, many of the phase change materials we're dealing with, we know their properties at room temperature, but when it gets to 6 or 7 or 800 degrees, we have no idea what the density is, what the viscosity is, what the specific heat is, and we are doing some work to actually measure these, and we are finding that many of the measured values are quite different from the values quoted in textbook or relying on some formulas to produce them. So this is the first hurdle. Then doing a lot of cycling to melt and freeze in an automatic way over a lot of time, accelerated cycling testing to make sure that the materials will last for many hundreds of cycles. Working with another university to look at the compatibility of the container and pipe materials, improving the heat transfer rate of the PCM, and you'll see a number of options to make this happen. The whole system design and evaluation we do through modeling and then through laboratory experiments, and some of these experiments we start at low temperature and then go to higher temperatures, and then we design and test the full prototypes. We're not saying that we're going to have a full size prototype like what that we'll have commercially, because we don't have the capability, but recently we've built a test facility for quite credible prototype sizes to ensure that the technology works and make sure that we can do control testing of small prototypes before we can say to industry they are ready for commercial use. And finally, economic as well as technical evaluation of the systems we are looking at. So now let me show you some of the materials we're dealing with or we're looking at. So when we look at temperatures in this region, 400, 500, 600 degrees, certainly carbonates are looking good, because not only they have a high melting point, but also they have a high melting and freezing enthalpy. So they store a lot of heat per unit mass, which is obviously good. And if I move, and you can see here in this slide the traditional salts further down around here, but we are aiming to go to higher temperatures and higher enthalpies. And if we go even to higher temperatures, we are looking at particularly some aluminium alloys or aluminium and other molten metals or metals that melt at the right temperatures, and some of these alloys around here you can see melt and freeze at 500 to 700 degrees, and we are looking at some of these as well, not only on their properties but their economics. These materials are good because they are better thermal conductors than salts that we looked at earlier. So these are some of the highlights of where we are at the moment. We are actually developing new methods for testing materials and finding their properties. We are identifying a number of materials that melt and freeze up to 550 degrees. We've done a lot of cycling of some of these materials. We're working on testing the materials with some metals and steels, particularly stainless steels, to see how they are going to operate in the long term. We are certainly looking at so many options for enhancing heat transfer and looking at designs, and finally we've established a facility for testing these designs. These are some of the materials we have actually tested, and we found some to be potentially possible, and some of them are better than others, and I think there's no time to go through them. We've also done some analysis of the cost and found it's not just the cost of the material itself that's important, but the cost of the container material and the vessel that will, and the pipes that will be using them, to get a full picture of the costing. And certainly some of the carbonate eutectic mixtures and the chlorides and the aluminum alloys are looking the best candidates for phase change storage materials. We are also doing some corrosion testing, which could start with simply putting the material in small crucibles and raising it to the right temperatures, but then it gets a bit more sophisticated and looks at the corrosion of some specimens when they are in contact with our PCM to see how they work. And we found some surprising results there, that some materials cause corrosion at 300 or 400 degrees, but when you raise them to 600 degrees or more, they don't corrode anymore, and they are quite possible. So we don't always need to be put off if we have problems at low temperatures. One of the options we are also looking at is having small amounts of the PCM encapsulated in some materials and using a packed bed, and that provides a large surface area for the heat transmission, and the melting and freezing happens quickly. And you can see here some failed experiments, and down here some better results after some testing. A lot of modeling using computational fluid dynamics. This is an example of trying to compare a real test over here with the model and the use of different size meshes to show how outward freezing happens around a coil, and how the frozen component increases within the vessel. There's more here, but I haven't got a lot of time. Another option we've looked at is this geometry of having 3 tubes with the heat transfer fluid being on the outside and the inside, and some fins. And this we did some modeling with using CFD, and then actually did some testing to ensure that it works. And the model actually is validated. And these are some of the results that show good agreement during the freezing cycle at the top and the melting cycle at the bottom. And it's difficult to see probably from the back, but there's good agreement between the prototype and the model work. Other activities is a lot of CFD analysis of different geometries And our focus has been most of the time on the so-called tube in a tank arrangement, where this is the simplest possible arrangement, where we have tubes, where we have the heat transfer fluid in a tank full of our phase change material. And we found various outcomes associated with the directions of flow and the geometry of the tubes to ensure that we get the best outcome. So we've also developed some simple design process and compared it with the CFD modeling for the use of the tube in a tank. The one possibility we are looking at, because we get quite a range of temperature output from the solar resource, we are looking at having what we call a cascade PCM system, where we are not using one material as the phase change material, but a combination of 2 or 3 in series, so that we get the best thermodynamic advantage of the heat source available. And this is one concept for 3 PCMs in series. Another one which I've already mentioned, and this is by simply circulating or pumping the liquid phase during the melting or freezing processes. Once we have some liquid phase, we can accelerate the processes and double the heat transfer rate and the melting and the freezing speed. And these are some of the experiments that we did to confirm the results of the modeling. And I'm not going to show you any results. Our latest design looks like this for a storage vessel with obviously the tubes in a tank. And we've developed 2 test rigs that use the tube in a tank concept, one at moderate temperatures, which are in the 400-degree range, and another one at higher temperature at the 600-degree range. And obviously the materials associated with them and the details of the design are a bit different. And these are some of the pictures of them. I think I know the time is running out, so I'm going to go very quickly. One of the last things I want to show you is a test facility that we've just commissioned for testing some of these prototypes. It's obviously a facility that doesn't use the sun heat, because we don't have enough a tower system nearby like some people might have. But we use electrical heat to generate quite a lot of heat and control the heat being fed to the phase change materials to freeze them, and then very closely monitor how they melt. And this is what the test facility looks like in reality, and how we are going to use this facility to test these. So as final comments, with more installation of solar PV and wind, certainly the size and the value of thermal storage will become more important. And you probably have seen that maybe initially the first systems that were built had very little storage, and now they are increasing in size. And I think with time, if we are going to have more and more contribution of renewables into the grid, we need larger and larger thermal storage system to make this possible. We can do that with higher temperature operations, particularly with the developments of the tower system, which are being accepted as the state-of-the-art technology. We are certainly developing and showing results both economically as well as technically, that the use of thermal storage using phase change material is possible, and we have found some of the suitable materials, and there's still a lot of work, but certainly we are on our way. And before I finish, I need to acknowledge my research team at the University of South Australia, which has a number of staff and a number of research students. We have about 30 people working in this area, and also my partners in the Australian Solar Thermal Research Initiative and the Australian government, which is funding this work. And please, if you are interested in more details or some publications, we have a lot of publications in this area. If you are interested in a particular area, please feel free to contact me, and this is my email. But also, if you want to look at either our website for the Barbara Hardy Institute or the ASTRI website, there's a lot of information. And with this, I thank you for your attention, and I'm happy to answer questions if we have time.